What's up, CoderBite? Welcome back to another Data Structures and Algorithms video. I'm Elizabeth, and this week we are kicking off our System Designs series. I'm really excited about this series because I think these are the kinds of questions that most closely mirror what you're actually going to be doing on the job. I don't know about you all, but at my company, on my team, we have architecture, decision, meetings all the time where we discuss how we're going to do something. We plan it in broad strokes before anyone actually gets into the actual building of whatever service we're designing. And honestly, they look a lot like what a systems designs question will ask of you. So I think this is actually really valuable in terms of practicing your skills as an engineer and also practicing for interviews. Without further ado, let's get into it. Okay, so before we get started with this week's actual problem, let's talk generally about system design and some of our general tips for, really crushing this interview and making sure that instead of just kind of a generic answer, you really understand the question, talk to your interviewer, and have a really good conversation. Ultimately, I think system design questions are really testing whether or not it's pleasant to plan something with you. Can you see broad strokes? Can you see at the edges of your design all of the, pros and cons of the design? And is it pleasant to talk to you about it, right? So system design questions, unlike algorithm questions, really are often not going to have that much coding. So it's important to understand what is the purpose of these questions and how can I actually fulfill that and demonstrate to my interviewer that I know what I'm talking about. So for my first tip, I think it's important to actually pretend you're on the job and designing a system, right? Like I said, these questions are often they're real world problems and they're going to be similar to some of the things you're actually going to design on the job. So it's useful to pretend that you're on the job, right? Pretend that you are at the company, you've already got the job, you've landed it, they pay you a lot of money for it, and you're actually trying to build a system that works, a system that you can be proud of, showing your manager, showing other teams, one that you're okay to continue to work on, right? We've all built code that it's like, I hope I never have to touch that again. Don't do that, right? Build something that you actually can manage afterwards, something that will actually scale. These are things that will set you apart from other candidates because I think it's not a one solution fits all. This is going to be something that is coming from your mind and you're going to introduce the interviewer to your mind. This is the opportunity to impress them with what you have to offer and say all about how you might plan something. So I think this is a really good opportunity to pretend you're actually on the job, right? Take off that interviewing hat, put on your engineer hat, and hopefully that's one that you're comfortable wearing. So that's tip number one. Tip number two, communicate clearly and in broad strokes first. Again, I said this briefly, all throughout this video already, but a big point of system design questions is actually to demonstrate that you know how to communicate around ideas. You know how to think of something and not only think of it and implement it, but think of it and communicate around it. Talk to your interviewer. And that is a very, very important skill. And again, something that will set you apart if you can really communicate around an idea. If it helps, imagine that the person you're talking to is less technical, and really like pretend that you are at the job, you're talking to a product manager, you're talking to someone who needs to use the system and is relying on you to build a good system. And you're kind of like selling your idea, right? So I think that knowing how to talk about something in a broad way before you get into the details of something is a really, really useful skill and something that is really important for this sort of question. This is another really important thing. Be open about potential flaws in your design. What do I mean by that? Often when you design a system in software, it can't check all the boxes. You're not going to get a perfect solution where there is no, sacrifice in some aspect of the system. Almost all solutions to a problem unless you have infinite time, infinite money, infinite resources. You're going to be having some compromise. And I think that it's really important to be open about those potential flaws. A mistake I see engineers make often is that they are so concerned with appearing like they know what they're doing and they know what they're talking about that they might present a design and then any sort of like potential flaw that someone points out, they're like, no, that's not a problem. And they shut it down, right? No, that's not a problem because blah, 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 blah. And maybe you're right, maybe you're not right. Often there are flaws. And I think that to be open about those from the get go is actually demonstrates your maturity as an engineer. I think being open and honest about the flaws your design might have really shows that you understand that there are often compromises that need to be made. And the important thing is to talk to your interviewer about those compromises so that your design makes the right compromises. And that might be a business decision, right? Like you might be at a company that only has 3 engineers. So your design has to account for the fact that you don't have unlimited people to work on it. And so you might make certain, decisions based on that. And you can't know that. Your interviewer is going to be the one who's going to kind of tell you what are the flaws that the company is okay with, bringing on in this system design. And if you're too busy trying to convince your interviewer that there are no flaws in your design, you won't really hear the hints that he or she might give you around what is important to the business and what is not. So that's something that I think is a really important thing to do and not something to shy away from. I think it's a very good thing when an interviewer says, this is my design, but I think that this is going to be a problem if we scale to this amount or whatever. So definitely don't be one of those people that thinks that they're perfect. That's also just a tip from me. Don't do that. It's not cool. State assumptions explicitly to avoid miscommunication. So this is another good one. Often when you're talking to someone about the design of a system, you're assuming a lot, they're assuming a lot, and often your assumptions are not necessarily matching up. And then you go to the demo and it's like, oh, you did it like that? That's not what I wanted at all. So I think that in system design questions, obviously the feedback loop is very short. You're doing it in just the time of the interview. Make sure you state as many of your assumptions as you can explicitly so that in the beginning of your design, you can make sure that you are only assuming things that are accurate. And rather than design a whole thing and then one of your assumptions, the interviewer is like, oh no, that's not how we do things here. And we're not, that won't work. And then at that point, it's harder to backtrack. This is the opportunity in your kind of outlining phase to state those assumptions off the bat so that things don't surprise you at the tail end. Don't get too married to an idea before you are ready yet, right? Talk about all this to your interviewer. And my last tip is to take ownership. This is an opportunity to really take the lead. You want to show the interviewer that you are okay with designing an entire system and talking about it, and you don't need someone to lead you the entire time. Because I think this is an opportunity to demonstrate maybe that you're less of a junior engineer, more of a senior engineer, depending on the position you're going for. You kind of want to show that you have opinions and you have have a plan and you know how to execute that plan. And if you're waiting for your interviewer to kind of be like, do this, I like to do that, use this kind of database, what's the traffic? I'll tell you what the traffic is. No, this is an opportunity for you to tell your interviewer, this is the plan. This is how I'm going to do things. Now, it's still very important to listen to your interviewer, right? You don't want to steamroll over everything they're saying, especially in the very beginning of the question when you're really interviewing your interviewer, right? You're trying to find out what do they need and what do they want and how can I do that with my system design? How can I accomplish it with my design? But make sure you're leading that conversation and that you're not kind of offloading that onto your interviewer. This is, again, an opportunity to demonstrate that you know how to look at a system from a bird's eye view. And I always say that this is kind of the difference between a very junior engineer to a more mid to senior level engineer. Someone who can see those outer edges and plan accordingly, and then work on the algorithms. So, food for thought. I think these are pretty good tips for probably any interview, but especially system design questions. This week's problem. Design a URL shortening service such as TinyURL or Bitly. So why did I choose this problem as our first systems design problem? Well, I think that this is a problem that it's like the quintessential system designs problem. I've seen it everywhere. It's almost everyone's hello world of system designs problems. And I wanted to pick a problem that probably most of you have seen or seen other resources around so that we can talk about kind of the framework of how I approach system designs problems in general. And then throughout the series, we'll do some harder problems and we'll use this same framework because I think this is going to be your toolkit. This is going to be kind of your step-by-step guide to how you actually solve any system designs problem. And we're going to do it with this problem that people have seen just to kind of get everyone used to this way of thinking. So let's take this URL, for example. This is a long URL, coderbyte.com / etc. blah, blah, blah. And basically, we want to design a service that gives us back a short URL, right? So in this case, we would have this short URL, this bit.ly, right? So every short URL will have the base URL in common. But the parameter afterwards is a, let's see, 1, 2, 3, 4, 5, 6-letter key, right? And this 6-letter key is going to map somehow to this long URL so that when someone hits this URL, they get redirected to the long URL. So that's the problem, right? I think everyone can understand that. It's a pretty straightforward, easy system to understand. So the first step for any system design problem is to scope the problem. This is the part of the interview where you kind of communicate around the edges of your idea. You talk about, what kind of users you're going to have, what kind of traffic, what the exact, parameters of the algorithm is, what can you and can't you compromise on, stuff like that. So this is your opportunity to ask your interviewer questions about the service. Interview your interviewer, just like you would if you were on the job, right? If you were talking to a product manager and they said, design this, and they didn't give you any acceptance criteria, they never give you enough acceptance criteria, am I right? This is where you ask all of those edge questions. You don't have to talk yet about the wires, how you're going to actually connect all the pieces. You have to understand, what is the purpose of this system? So for this URL, you might ask, will people be able to specify their own short URLs, or will they always be auto-generated? How many URLs can we expect to need to generate a day? Do we have to track any statistics related to using the URL, such as like how many clicks and whatever? Do the URLs need to stay alive forever, or can they expire? So this is an opportunity to ask your interviewer these questions, and ultimately you want to come out of this first step of a system designs problem with a list of major features and use cases of the service that you're going to have to incorporate into your design. These are your non-negotiables. Your system has to do these things. So this is almost going to be like almost outlining where you're going. Where's your North Star, and where do you have to have your system, what do you have to have it actually accomplish, more than just the short question prompt, right? Like, we need to know all of the things besides for create a short URL from a long URL. So out of scope the problem, you want to come up with a list of major features and use cases. And then I would also say that in this step, you want to talk to your interviewer about system availability requirements. Now, why do I say you should talk about this at the beginning? I think that this often will inform a lot of other decisions you make. If you know that your system has to be highly available, and you know that it's going to be read heavy, let's say, or whatever, you know that you're going to have a lot of users, you know that you're going to have a lot of actual data, that is all going to inform the rest of your components when you start to get into, it's almost like with a system designs question, you go from the outer edges and you move closer and closer to the core algorithm. And all of these things that you're asking about in this outer realm are going to inform some of your decisions that you make as you move closer to that center core of your algorithm. So again, I think system availability requirements definitely might change how you plan something and how you actually, what kinds of technology you use, your algorithms, etc. We'll get to it, but these are kind of the ideas that you want to have in your mind at this stage in the process. So let's bring it back to our problem, TinyURL. So let's see. Features the service must have. Shorten a URL to a TinyURL. Okay, that we understand, right? Analytics for the TinyURL. Okay, we're going to have to track some kind of analytics related to, how many people, whatever, this might be a little bit more general, but your design has to be able to handle tracking analytics of whatever kind. So we have to retrieve the URL associated with the TinyURL, right? So when we get that short URL, we need to be able to know what URL was it mapped back to so we can actually redirect the user. And then we want user accounts, right? We want somebody to be able to log into our system, create a TinyURL, and then they're in the system. Those are their TinyURLs. So those are kind of just the broad strokes features this service must have. Now, let's talk about some of the system availability requirements. So in this situation, our system needs to be highly available because if the service is down, the URL redirections will start failing. And then it's unusable. Very quick, no one will use our service if sometimes they click the short URL and they don't get to the long URL. They'll just use the long URL, right? So we have to make it like really work and really always work. This is a sort of system that our users probably will have a very low tolerance for the system not being available. The other thing is that URL redirection should happen in real time with minimal latency. Again, our users are not going to use our service if they use our TinyURL and it takes much longer to get to wherever they are trying to go than the actual URL. No one's going to want to use our service if we have even a little bit of latency there. So we have to make sure that this is happening in real time. So this is an example of the features and system availability requirements that will inform as we go closer to the center of our core algorithm. Step 2, capacity estimation. Now, again, this is a beginning step because I think that the capacity estimation helps to inform the rest of the algorithm when we start to talk about the actual components of our system. If we're going to have to store a bunch of data, we might use a different kind of database than if we don't, right? Or if our data has a bunch of, we're going to have a really read heavy but not write heavy experience, that also might inform what components we choose to use. So this is an early stage kind of broad scopes trying to understand what are the system's requirements. So this is really just a second step of finding out what about our system is a non-negotiable. So for our system, let's do our traffic estimates. Now, this is the traffic the site is going to have, right? The usage of the actual service. So our system is going to be very read heavy. There's going to be significantly more redirect requests, right? Someone coming with the short URL and wanting to go to where the long URL goes compared to new URL shortenings. So we're going to have a bunch of people clicking those short URL links needing to be redirected as compared to people actually creating new short URLs. So this is going to be a read heavy service. Let's assume that there is a 100-to-1 ratio between reads and writes. So what that just means is that there's going to be 100 someone might ask for a redirect from a short URL to a long URL 100 times for every one short URL that someone generates. And I think it's important here, pick numbers that are easy. This is a broad strokes kind of conversation. So don't pick like 63 to 1. Don't do that. It just doesn't, you're not going to be able to do that on the spot unless you can, and then, you do you. But I try and choose like, numbers that are easy to work with, and just pick numbers that make sense. So let's say you can do like orders of magnitude, right? So if this was a less read heavy, situation, you can do 10 to 1. That would be significantly less than 100 to 1, but it's still easy to work with in terms of the number 10, right? Versus 100. But here, let's assume 100. Assuming we have 500 million new URL shortenings per month, we can expect 100 times 500 million, right? Because we're going to have 100 to 1. And if it's 500 new URL shortenings, we have to multiply that by 100 in terms of what we're expected to be able to handle in terms of redirects. So we can expect to have 50 billion redirects per month. Now, new URL shortenings queries per second. So that is going to be, right, we're going to take that 500 million, right, which is per month, and then we're going to divide it by 30 days a month times 24 hours times 3,600 seconds. Now, 3,600 seconds are the amount of seconds per hour, I think, right? So 60 times 60 is, 3,600. So that's how I got all of those numbers. And you just divide that, right? If we're having that many per month, that means we're asking for 200 approximately new URL shortenings per second. Now, how many URL redirects per second? We take that same 200 URLs and we multiply it by 100, right? Because again, we have that nice easy ratio to deal with. So here we have 100 times 200, which is we got from the question before, and that becomes 20,000 URL redirects per second that we're going to have to be dealing with. So again, very read heavy, a lot of requests per second. Now let's talk about some storage estimates. These are generally the two capacities that you're estimating, traffic and storage. So if we have to store a shortened URL for 5 years, now this is something that I meant to write in a previous slide, but this is something that you talked about with your interviewer, right? That we are only ever storing a URL for 5 years. After that, it expires. So if we have to store a shortened URL for 5 years, the total number of objects we can expect to have to store is 500 million, right? So because we have 500 million new URL shortenings per month, times 5 years, right? Because we just said times 5 years, times 12 months is 30 billion. So we're going to have to store 30 billion shortened URLs at any given point. That's going to be approximately the amount of data that we'll always ever have, right? Because at 5 years, they're going to have to renew or recreate the URL, or we're just going to expire it out. So that's going to be 30 billion. And then here I just have, again, I want to very much stress, use easy numbers here. It doesn't look good if you start to do all of these calculations and you can't do them, right? And it's not necessary. Don't make yourself look bad for something that it's not so impressive if you're really good at these like multiplication kinds of things, because in general you'll have a calculator, it won't matter, right? So don't even trip yourself up here. Try and use easy calculations. Remember, these are estimations, broad strokes, right? So that's just something to keep in mind. So here we have our traffic estimates and our storage estimates, and I would suggest that you keep this on the whiteboard, again, because we're going to refer back to these numbers when we start to make some other decisions regarding our actual components as we move closer to that core algorithm. Next up, database design. So I think that depending on the problem, these steps might come in a few different orders. But for this one, I think database design is a really nice, segue into kind of going from the broad strokes to the more specific components of the actual, system. So I think often with any system design, there's going to be a data component, and accessing that data is going to be important. So this is where we're going to kind of use the information we've gathered from step 1 and step 2, and we're going to kind of create some schema, right? We're going to say, like, this is how I think we should store the data, and this is why, right? Because it hits a lot of the things that we've talked about in steps 1 and 2. So use the information gathered from steps 1 and 2 to inform how you store the data. We already know we have to store billions of records, right? We discovered that already in that other slide. Each object we need to store is relatively small, right? We're only ever really storing the short URL and the long URL and like maybe the user that created it. And then we might have some other table that's tracking some statistics, but ultimately that can just, have a foreign key to the small object, which is the actual, long URL to short URL. So each record is going to be fairly small. The only relationship we need to store between objects is between the URL and the user who created it. And I didn't write this here, but maybe that analytics table. But again, I think that is going to be something that is kind of superfluous. We'll get to it, but it's going to be a part of the system as another table, but it's not really the core of what the system has to accomplish. So it's just going to be those long URLs, short URLs, whose is it? And our service is read heavy, right? Very read heavy. So we need to be able to access things very quickly, more than we have to insert things very quickly. So here is an example of a table, our URL table. And I just used, I have the ID is a primary key, right? And that's an integer. And then we have our key, which is going to be the short URL key, right? The parameter after the beginning part of the URL. The original URL, which is the long key. These are both strings. We have a creation date, which is a date, an expiration date, which is a date, and then a user ID, right? That's an integer. And here's our users, and I just have a primary key of user ID with a name and an email, which are both strings, and a creation date, which is a date. Now, this format that I have here is DynamoDB. If you recognize that I have that like PK and all of these data types kind of look like DynamoDB. So it is DynamoDB. Now, why did I choose DynamoDB? Because you're going to have to explain why you're choosing what you're choosing. Number one, there are minimal relationships to represent. Instead of doing something like, SQL or something that you can easily express relational data, there's no need for that because we really don't have very much relational data. There are no really complex, it's just URLs, and then we can just attach the user IDs to whose URL it is. The other reason is that with DynamoDB, because it's a NoSQL database, we can easily store billions of rows. We can just insert and insert and insert as much as we want. So it's a really good option for this sort of problem. And again, I think make sure you can explain why you're choosing the database you're choosing. So here, these are my 2 reasons, but think about other reasons why you might use this and be able to kind of defend your choice. Okay, number 4, system APIs. So this is where you're kind of doing an overview of what is the agreement between your system and the rest of the components? What are the operations that we're going to have to be doing, and how might we create an interface for that? So this is an opportunity to, again, talk through the API with your interviewer. Does a REST API make sense for the system? Write out some of the common operations you'll need for the system. So, do you want to make a REST API? Do you want to make an RPC API? Do you want to make, do you want to make a library that other code can then use? Talk about this with your interviewer and start to design the edges of the actual system. So for ours, I think we're going to want to definitely be able to create a TinyURL. So let's say that might be a post, right, to /TinyURL with a body of URL with the long URL and the expire date, which is optional, and it defaults to 5 years from now. So I just have that as a timestamp but this is what a request might look like to create a TinyURL. Delete a TinyURL, it's a delete request with the key after the TinyURL, and again, this is clearly a REST API. Get a TinyURL, to get request to TinyURL with the key, and then a redirect to the original URL. This is going to be a get to just the key, right? So this is going to be the part where it's like tinyurl.com or bit.ly or bit.ly / the actual 6-letter key or 6-character key that will redirect to the long URL. Okay, we are up to our core algorithm. Finally, we are headed towards the center of our algorithm. So when you talk about the core algorithm, this is going to be potentially the opportunity that you have to code, right? This will be the only kind of piece where you actually might have to like get on the whiteboard and actually write a function. So for us, generating the keys for the TinyURL is the core algorithm, right? That's the part that we can design the whole system, but if we don't have a way of generating those keys, then what's the point, right? So here are some requirements. It has to be fast, right? Because we don't want to have a system that it takes so long to create a TinyURL that people are just going to use the long URL. It has to be unique. Each key has to be unique because we want to redirect only from one small URL to one large URL. Short to long, I don't know, whatever. And we want to create these short strings, right? Otherwise, there's no point in our entire service if we're just giving you also a long URL. Long to long, we could do without it. So in how I would do this is I would probably have a key generation service. I would have, outside of kind of the server that's managing the requests for new keys and redirects, right? And outside of the database that's storing all of this, I might have a separate service that's entirely just for generating these keys. We can generate the keys in advance for quick retrieval. So that way, as soon as someone requests one, we have one available. We don't even have to send anything, do any whatever. The key generation service will also keep track of the used and available keys, right? So we're going to have some sense of how many keys do we have to generate, how many keys need to be available at any given point. This is going to be an opportunity to look at all of those, estimations that we made before for capacity. And we're going to have to see how much should we have available and how should we manage this, right? Because it depends on how many users we have at the end of the day. But this key generation service is going to keep track of the used and available keys. And yeah, so let's talk about how we do this. So right now, each of our URLs is going to have an ID, right? We define that in our database design. So why can't we just use the IDs as the keys? So the IDs are going to be integers, and they are going to be base 10 integers, right? So the way you have to determine how many different combinations we'll be able to have with base 10 encoding is you take the base, right? So this would be base 10 because it's an integer, and you raise it to the power of however many letters we have in the string. So in this particular instance, we want 6. We want 6-character keys. So that means we have 1 million unique 6-letter strings that can come out of the digits 0 to 9. Now, according to our capacity estimation, that's not enough, right? We need billions of options. We can't just use those IDs. So how can we kind of make this number bigger? Well, we can raise, right? We're still going to have this 6-letter string, but we can make it a different base, right? We can have a different base encoding. So we can change this number to be a bigger number and then get more options for unique keys. So let's say we have a base 62 encoding. Base 62 encoding is the letters A through Z, capital and lowercase. So that's 26 plus 26. So that is, let's see, 40, 52. And then it is the digits 0 to 9. So that's 62. So that's how we get the 62 characters that are potentially options for this encoding. So then we raise 62 to the sixth, and we get approximately 56 billion unique 6-letter strings, which is plenty. I believe if we go back to our other slides, we only needed 30 billion. So this should be plenty for us. So that's great. So let's look at our key generation service. So here's our client. Here's our key generation service, right? And then here we have these two different tables where it's the available keys and the used keys. And essentially this key generation service is going to be generating, maybe on a cron job or something, all of the available keys, and then cycling them between these two different tables, available keys and used keys, depending on as people create URLs, and then as the URLs expire or they get deleted, they go back into the available keys option. And this should keep us going for a while, right? Because we've now created this very large ceiling of how many unique keys we can have. So how do we actually take that long URL and encode it with base 62 encoding? Now we're finally going to code. Let's do this. I think you all are familiar by now. All I've done is fill out some test cases for us for this base 62 encode function that we're going to write together. So here I have some numbers, and what we're hoping to get back is up to 6-letter strings that are keys, which will represent, the base 62 encoded version of these base 10 integers. So to get started, let's write that function, base 62 encode. And now this function is going to take a, base 10 number, right? So let's write that in as base 10. And essentially, this is kind of a common way of encoding something. And if you've never seen this before, I highly suggest you Google how you would encode a base 10 integer into a binary, digit or whatever, and any other kinds of encoding. But it's all relatively the same. So we'll go through it briefly, but you should definitely check that out online if you've never seen this before. So the first thing I want to do is have some sort of string, right, that we're referencing as our base 62 characters that we have to choose from. So we can say const base 62, and this is just going to be our string. As we said, this is the letters A through Z, both capital and lowercase. So let's see if I could do this real quick. A, B, C, D, E, F, G, H, I, J, K, L, M, N, O, P, Q, R, S, T, U, V, W, X, Y, Z, and then the same thing, capital A, B, C, D, E, F, G, H, I, J, K, L, M, N, O, P, Q, R, S, T, U, V, W, X, Y, Z. Hopefully I didn't miss any. And then we do our digits, right? Our 10 digits, 0 to 9, 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. So these are basically, this is what we have to choose from when we're going from our base 10, which is, remember, 0 to 9, for base 62, which is all of these options. So that's our base 62, right? And then let's say let encoded, and let's make that an empty string because we're going to return that. That's going to be our encoded base 10. So what do we do here? So when you're encoding something, generally what you're doing is you're building whatever the new thing is from the right side to the left side. So the least significant digit, it's not a digit here, but it might as well be, the least significant digit to the more significant digits. So the first step for any encoding is you take the base 10, right, whatever you're trying to encode, and we want to get one of these, right? We want to map whatever this is to whatever this is. And the way you do that is by using the modulus operator. I believe that's the full word, but everyone says mod if you're cool, of course. So you use this modulo, I don't know, someone write it in the comments, operator. And what that does is it gives you the remainder, right? So we're going to make a division. We're going to divide that base 10 by 62. And the remainder of that is going to be the letter that we take, or the number, the character that we take and put in our encoding. So what is that going to look like? that is going to look like this. We're basically going to say that encoded is going to equal whatever that base 62 is at, right? We're going to take the character that is at whatever gets returned from doing base 10 mod 62. And the mod 62 here, the mod 62 is whatever the encoding is we're trying to go towards. So the 62 is because we're trying to encode the base 10 in base 62. If it was, excuse me, binary, we would have a mod 2. And this gives us the remainder. So I'm going to log this out, I think, so that everyone can see this. And that way we can look at what's happening here. And then we want to not overwrite whatever we have so far. We actually want to just put it at the we want to put it to the leftmost spot. So in the first iteration, this is just going to be an empty string, but eventually this is going to be all of our encodings. So we want to, again, have those, we're doing this from right to left, from least significant digit or spot to more significant. So that's what that is. And then what do we do with that base 10? We update our base 10 to now be the base 10, right, whatever it was, divided by 62. And we're going to floor that. We want an integer value for this. And we're basically going to do this until we get to 0, until base 10 is no longer, and we've divided down enough, and we've encoded our entire base 10 string. So we're going to floor this. And I'm also going to log that out. Okay, and we are going to do this until, right, until this becomes 0. So let's put this in a while loop. Okay, and that is actually it. This is an extremely simple, algorithm. If you don't know how to do it, it's obviously, I don't know how you would figure this out intuitively, but if you know how to do it, it's very simple, it's pretty straightforward, and it's a very short little function here. So let's see our logs. Let's make sure we get what we hoped we would get. And we didn't get anything, so that is excellent. Oh, that's because I did code. I always do that. Okay, so we got a lot of logs here, so I'm actually going to not do this at first. And here we have our encodings. Now, this is longer than 6, probably because this is a giant number, right? It's too big. But if we, right, make it a little less, and this is also larger, so because remember we only need up to, I think it was 56 billion or something, right? That's what we're expecting. So this is all, these numbers were too big. They're producing things that are bigger than 6 characters. But now let's see what we get here. And we get 1, 2, 3, 4, 5, 6. Yeah, we get some 1, 2, 3, 4, 5, 6. And then this one is shorter, but that's all right. So that's the encoding, right? So these strings are representative of these base 10 things encoded as base 62. And now I am going to make this maybe a little smaller of a number so we can really see what's going on. And we'll put those logs back in. Clear, give us some space. Okay, so this actually only goes one time, right? So we have base 62, whatever the base 10 is, mod 62. So what that is going to be, that's going to be base 10, which is that first 16, mod 62. So let's do this together. And here I'll show you guys my calculation here. 16 divided by 62, right? So it goes in only 0.2 times. So what we actually get here is we just get a Q because it doesn't even go in once. So we take the remainder of what happens when you divide those two things, which you wouldn't see in Alfred. So let's actually maybe show it here. So let's say 16 mod 62, and we get 16, right? That's the remainder of dividing those things together. And then we take the thing that is at 16 in this base 62 encoding, which is Q. And that's the encoding, right? So let's take a slightly bigger example, something larger than 62. Let's take 150 maybe. And the first thing we get is 26. So we grab whatever's at 26, which is A, right? So that's here. And then you can see that this becomes the least significant digit. And then we divide again by whatever 62 divided by 26 is, which is 2 and change. And then we do 2 mod 62, right? So 2 mod 62 will be, let's see, 2 mod 62 is 2. So that's how we get that C, right? And then we are at the end. So that's how you encode stuff. I think it's pretty cool. And yeah, play around with this with different bases and different things, but this is the core algorithm of this, which is actually kind of nice because it's super simple if you know how to do it. And I think we're at our last step. This is step 6, and it is all about load balancing and caching. Often I find if you've done the first 5 steps well, this part is obvious. You'll know exactly where you need to load balance and exactly what you can and can't and should cache. So for this example, let's talk about caching first. We can cache every request for a TinyURL redirect that we receive to avoid checking the database each time we get a request for a TinyURL. This will help with our speed, our latency, and it will just overall make a better experience for our users. We can load balance as well. Where can we load balance? Often you're load balancing between different, I would say, components of your system. And you want to kind of talk about load balancing in terms of, I'm putting a load balancer between this and this, right? So where can we load balance between for this? We can load balance between the clients and the application servers. So this is going to be all of the requests that we're getting to create URLs and to, get redirects. We can load balance between the application servers and the database servers. This is going to be between, let's say, the server that's handling those REST requests to get and, create URLs, and the actual database servers themselves, depending on how you have it organized. We can also load balance between the application servers and the cache servers. So this is the point in the, diagram where you are checking there's a cache being kept somewhere, and the application is like, hey, do we know where this goes? This URL needs to redirect. So we can load balance even before it gets to that cache layer. So those are kind of the opportunities you have in this scenario to load balance and cache. But this is always a really good opportunity to also kind of know whether your design was a good one or not, because you should be able to load balance and cache somewhere. It's just a matter of finding out exactly where and how. Let's put it all together. Here is an example. This is kind of a loose diagram of what it might look like to access a TinyURL. So this is getting that redirect, right? This client is getting the short URL, but he really wants to go to the long URL. So they send a request, access a TinyURL. It gets to our application server. This is maybe where this is a REST API. And I'm saying, hey, get me the long URL associated with this short URL. So this server can talk to the cache. And again, remember, there might be load balancing here, here, and here. So this server says, find the original URL in the cache. If it's found, great, send it back, right? URL found, redirect to original URL. If it's not found, go to the database, find the original URL, and then send, appropriately whatever the responses are if the URL is found or not found. And of course, update the cache, right? If we have already made a request, we now want to save that request so that next time a user accesses it, we don't have to go through this database step. So that's a good kind of overview. And often in these sorts of problems, you will want to diagram out a little bit kind of the system design, right? This is the system that you've designed. So be ready to kind of make this sort of drawing on a whiteboard. Now let's look at what it would look like to create a TinyURL. So here's our client. They want to create a TinyURL. So it goes to the server. First, it goes to the key generation service, which remember might be generating keys on a cron, moving things from available keys to used keys, whatever. This is kind of running as its own service. So we get a unique key, right? And we then return the unique key and create in our database a record with the ID, which is mapped to our key creation, and the URL. Now, of course, we're doing an encoding, right? So we want to map whatever the ID that it has in the database to the key that we've generated in our key. So you might talk to your interviewer a little bit here about how you might go about doing that. You might want to save the record in the database first and then go to the key generation service and get one. You might want to get the whole key generation object, which is the ID and the encoding, and insert that entire thing into the database, but you can talk about that with your interviewer. After it's created successfully, we can then return it, and we're done. That's our system. I hope you all enjoyed our first video in our systems design series. We're going to do a bunch more of these, so get excited. We're going to talk about all different kinds of systems, and we're going to try and use this framework that we've established here today to kind of give you a toolkit so you never walk into a system designs question afraid again. I really love system designs questions because I think that it's actually what we're trained to do as engineers rather than the algorithm questions, which are a little bit kind of neither here nor there in terms of what we actually do on the day-to-day. So join me next week. We're going to do another cool one, and I hope you really enjoyed this. Have a good week, everybody.